So, welcome to today class of nonlinear vibration. Today class we are going to study few examples related to parametrically excited systems. So, previous classes we have studied about the free and force vibration of nonlinear systems, and today class we are going to study about the parametrically excited system, which differs from the force vibration of a system in mainly two different ways. So, we can have a forced vibration system and parametrically excited system. Let us see what is the difference between these two. Forced vibration. So, parametric excitation is also a kind of force vibration, and in this, so forced excitation and parametric excitation. So, let us take a cantilever beam, and so if we are applying a force, let us apply a force in this transverse direction, that is p sin omega t, and the vibration will take place in this direction. So, the direction of application of force and the excitation or the response takes place in same direction in case of the forced vibration of the system. And also in this case we have seen that when the frequency equal to the natural frequency of the system, then the system have a resonance condition. So, system attains a resonance condition, but in case of parametrically excited system, so let us take this same cantilever beam and let us apply one axial load. So, in this axial load, let me apply this is equal to P s plus P d sin omega t. So, in this case, as we are applying a axial load, as we are applying an axial load to the system. So, if it exceeds the Euler buckling load, then it will start buckling, but when a dynamic force is acted to the system, then for some value of this dynamic amplitude of the load and the frequency omega, so it will start buckling before it attain the critical Euler buckling load. So, if we are applying only the static load to the system, then when it is equal to this Euler buckling load, it will buckle, but when a dynamic load is added to the system, it will start buckling or it will start vibrating in a non-trivial state when this P d and omega, that is the amplitude and the frequency of the excitation term. So, depending on some value of this amplitude and frequency of this excitation term. So, we have to find for what value of this P d and omega the system start vibrating in a non-trivial state, or the system becomes unstable in the trivial sense. So, in this system, so it is very important to find the parametric instability region, that is, if we plot a curve between this P d and omega. So, we can find a region for which the systems will become unstable. So, this is the unstable state. So, this is the stable state and this is the stable state. So, in this study mainly our focus will be to find the parametric instability region of the system. Also, one more difference between this forced and this parametric excited vibration is that in the first case I told that this direction of the forcing and response takes place in the same direction, but in this case though the force is applied in the axial direction, the response will take place or it will vibrate in the transverse direction. So, it will vibrate in the transverse direction. So, the applied forcing and the response are orthogonal to each other, and also it will take place at a frequency. So, this parametric excitation will take place at a frequency omega. So, this will be equal to omega m plus minus omega n of the system. So, when m equal to n, so this is known as principal parametric resonance, principal parametric resonance condition, and when m not equal to n, then we will have two conditions. So, one will be omega m plus omega n. So, where m and n are the mth and nth mode natural frequency. So, in this case when you are taking the sum type, so this will be combination resonance of sum type. So, this is combination resonance of sum type, and another one when omega equal to omega m minus omega n. So, this is combination resonance of difference type. So, already we have studied the equation governing this type of system. So, that is mainly known as Matthew-Hill type of equation. So, in case of the Matthew-Hill type of equation, the equation can be written in this form, that is q double dot plus q plus, if we are adding damping to the system, it will be 2 epsilon zeta q dot plus. So, we will have a term, this is q sin omega. So, we will have a term, this is f sin omega t. So, this will be the coefficient of q and this will be equal to 0. So, if we are not considering the nonlinear terms, then the most linear equation will be in this form and it is known as the Matthew-Hill equation. And already we have studied this equation, or we know how to solve this equation by applying different methods such as method of multiple scales or method of harmonic balance, method of averaging. So, we can use different methods to find the solution of this, or we can find the transition curve which separate this stable and an unstable region for. So, for this for some value of f and omega. So, this is the instability region. So, we can plot. So, this equation is in the form of Matthew-Hill equation. Matthew-Hill equation. So, today class we will take a multi degree of freedom system. For example, we will take a sandwich beam and we will apply. So, we will take a sandwich beam with a different boundary condition. So, this is the sandwich beam. So, in the sandwich beam, so it may have different boundary conditions. For example, let us take a boundary condition like this, and we will apply this periodic axial load. So, the periodic axial load will apply and we will find the resulting response of the system. So, particularly the sandwich beam consists of this skin layer, and so these two are skin and we will have a viscoelastic core. So, it will contain skin to skin. So, the skin may be of metallic type, the skin may be of composite material, or the skin may be of functionally graded material, and this viscoelastic core may contain this rubber material, or recently people are using this magnetorheological elastomer, which is in short known as MRE, magnetorheological elastomer. So, one may use this magnetorheological elastomer patch also in this viscoelastic core, and by applying this magnetic field one can increase the stiffness of this magnetorheological elastomer and increase the stiffness of overall structure. So, today class we will study about, or we will develop the equation motion of a parametrically excited sandwich beam with soft core. The core may be soft or it may be stiff. So, when it is stiff, then the displacement of top and bottom layer will be same, and one can use this antiplane concept or classical sandwich beam theory, and if the core is considered to be soft, then one can take higher order theory to derive the equation motion. So, let us first derive the equation motion of a sandwich beam. So, a sandwich beam, so it can be of a ordinary sandwich beam or it is a semi sandwich where we will have one single skin and this is the viscoelastic layer. So, one can have multi-layer sandwich beam. Also, the sandwich beam may contain foam type of, so it may contain this viscoelastic rubber type of material or soft foam type of material. So, this core may be of different constructions also, this may be honeycomb type also, one may use this honeycomb core and many other different types of core. So, example of some of the sandwich beams. So, human skull is a natural sandwich beam and so these are carbon fiber faces, one can use this honeycomb core. So, this is a section of the helicopter blade where one can use this sandwich beam. Similarly, this is a balsa wood core Kevlar face, also this is foam face with aluminum. So, foam core with aluminum face and one can use this magnetorheological elastomer also. So, as the core material. So, in case of the magnetorheological elastomer, so in this either in natural rubber or in the silicon rubber. So, one can add the carbonyl iron particles and apply a magnetic field during curing process. So, if one apply a magnetic field, then these iron particles will align during curing and they will subsequently increase the stiffness of the system. So, the elastomer, one can note that these elastomer are solid substances unlike this magnetorheological fluid MRF. So, in case of magnetorheological fluid, so which will act as a damper. So, this magnetorheological fluid will act as a damper. So, there in case of magnetorheological fluid, so in this fluid these iron particles are embedded and then one apply a magnetic field. So, then one apply a magnetic field to align the iron particle, the iron particles will be aligned and in that case it will act as a damper. Also nowadays some researchers are also working or using this magnetorheological fluid inside the sandwich structure. So, in between this viscoelastic layer one may use, so one may use this magnetorheological fluid also. So, in case of fluid, so it will used as a damper by applying this magnetic field, but in case of elastomer when this magnetic field is applied, so it will increase the stiffness. But today class we will study only on the soft core only soft core sandwich beam. So, already I told you there are mainly two different types of sandwich beam theories. So, one is the classical theory and second one is the higher order theory. So, in between one may also use the superposition theory, but mainly this classical theory tells. So, this is the primary deformation and secondary deformation of a beam. So, this combination of deformation one can find, this the total deformation one can find, but in case of classical theory, so it is assumed that the core is stiff and one can use same transverse deflection for both top and bottom layer. But in case of higher order theory, so this is this and this. So, this is the core part. So, this is the undeformed. So, this is the undeformed sandwich beam. So, now let us take the deformed sandwich beam. So, this is this and this is the deformed sandwich beam. So, here, so this is the core layer. So, this is core and this is the deformed sandwich beam. So, in case of soft core, so the top layer and bottom layer deflection will be considered to be different. So, one can take this top layer deformation as W t and bottom layer deflection as W b, and one can find the deflection of the core layer with respect to this top and bottom layer. So, there are many literature available on this sandwich beam. So, particularly one can see this paper by this Asnani, Nakra, Kaur Sujata, Frostig Barua. So, in 94, 95. So, they have used this hierarchy theory. In case of Kaur and Sujata, so they have used Kaur, Sujata and Ray and Kaur. So, they have used classical theory. Frostig Barua, they have used this hierarchy theory. Also, there are many other paper by other authors which considered mostly classical and hierarchy theories for the sandwich beam. So, let us see the mathematical modeling of this sandwich beam. So, here a force P 0 cos omega t is applied. So, let us take a unsymmetric sandwich beam with simply supported at the ends. So, it is subjected to axial force of P 0 plus P 1 cos omega t. So, P 0 is the static force and P 1 is the amplitude of the dynamic force with frequency omega. So, this is the core layer. So, we can consider both aluminum and steel for the skin and viscoelastic foam type core for this sandwich beam. So, let us take these are the assumptions. So, skins are modeled as ordinary beam with negligible shear strains that follow Euler-Bernoulli assumptions and are subjected to small deformation. The transversely flexible core layer is considered as a two-dimensional elastic medium with small deformation, where its height may change under loading and its cross section does not remain planar. The longitudinal stresses in the core are neglected. So, the interface layer between the phase sheet and the core are assumed to be infinitely rigid and provide perfect continuity of the deformation at the interface. So, taking these assumptions, now we can derive the equation motion of the system by using extended Hamilton principle and by writing the kinetic energy of the system and potential energy of the system. So, this is the sandwich beam, considered sandwich beam. So, this is the neutral axis of the top layer and this is the neutral axis of the bottom layer. So, W t, that is the deformation of the top layer, is with respect to this neutral axis, and W b also the transverse deflection of the bottom layer with respect to this neutral axis. And one can write, so this is the z direction and this is taking this as z direction and this as x direction. So, we have taken this dt as the thickness of the top layer, dB as the thickness of the bottom layer, let C is the thickness of the core. So, one can take a symmetric sandwich beam where the both top and bottom layer thickness will be same, or one can take an unsymmetric sandwich beam where the top and bottom thickness will be different. So, now, so these are the, so as we are considering only plane, as we are considering Euler-Bernoulli beam theory, so it is subjected to pure bending. So, we are considering the case when the system is subjected to pure bending only. So, here the forces are shown, forces and moments are shown in the top and bottom layer, and so this is already it is shown the deformed and undeformed shape. So, this is the deformed undeformed and this is the deformed state. So, here u t and u b, so are the axial displacement of the top and bottom layer. So, u c is the axial displacement of the core layer. So, one can write, so this is the shape before deformation and after deformation. So, now one can write the kinetic energy of the system as the kinetic energy of the top layer plus the kinetic energy of the bottom layer plus the kinetic energy of the core. So, the kinetic energy of the top layer can be written as m t into u t dot square, u t is the axial displacement and w t is the transverse displacement. Similarly, for the bottom layer can be written this way, and for the core it can be written. So, rho c. So, dV is the volume. So, that will give the mass and it will be the axial velocity. So, u t dot, and this is the transverse. So, this is due to axial displacement and this is due to transverse displacement taking the velocity term. So, one can write the kinetic energy of the system. So, here from this figure, so one can write this u c, that is the displacement of the. So, u c the displacement of the core layer as in terms of the bottom layer and top layer axial displacement. So, u c can be written as u b plus d b by 2, d b is the thickness of the bottom layer. So, d b by 2 into del w b by del x. So, this is del w b by del x plus u t minus d t by 2 del w t by del x into 1 minus z c, z by c. So, 1 minus z by c. So, z. So, at a distance z from the bottom layer. So, if we are finding what is u c, that is the displacement. So, we can write the expression in this way. Similarly, this w c that is the transverse deflection of the core can be written in terms of the transverse displacement of the top and bottom skin. So, it can be written as w c equal to w b minus w t into z by c plus w t. So, it is w t plus the additional term this. Similarly, the core layer axial displacement can be written as the displacement of the bottom layer plus this is the additional term. So, writing this core axial displacement and transverse displacement in terms of that of the top and bottom layer. So, one can write this equation for this kinetic energy of the system. Similarly, the internal potential energy of the systems can be written using this stress and strain. So, for the top layer it is equal to sigma x x into epsilon x x into dV. So, this is strain energy into dV. So, that will give you the potential energy or internal energy for the top layer. Similarly, for the bottom layer one can write, and for the core as it is assumed that the core is subjected to shear. So, the core is subjected to shear. So, it can be written the strain energy due to shear can be written using this shear stress and shear strain, and also due to this longitudinal stress and longitudinal strain. So, the core is subjected to both shear and longitudinal strain. So, one can write this total internal energy of the system by using the internal energy associated with the top layer, bottom layer and due to the core. Now, as the axial load is applied to the system. So, as we are applying a axial load. So, this is the axial load applied to the system. So, one can consider a small deformation of the system and taking this in extensibility condition. So, one can write the work done due to this load equal to half 0 to L integral 0 to L P into del W by del x whole square. So, in this way one can find the non-conservative work done and also the potential energy and the kinetic energy. And now, by using these terms in the extended Hamilton principle, so which is written as integration T 1 to T 2 delta L plus delta W n c dt equal to 0, where T L equal to T minus u. So, by taking this q k as the generalized coordinates which vanish at T 1 and T 2. So, one can find the equation motion. So, now one can find a set of equation motion in terms of W t, W b, u t and u b. So, one can get, so taking this q 1, q 2. So, we will have 4 q, q 1, q 2, q 3 and q 4. So, taking these 4 q generalized coordinates as W t, W b, u t and u b. So, one can find a set of equation governing equation motion. So, in terms of by taking the term which So, when we are applying this Hamilton principle, so we will have this term. So, integral T 1 to T 2 some term with delta W t dx dt. So, the coefficient of delta W t dx dt will be the first equation. Similarly, the coefficient of delta W b into dx dt will be the second equation. Similarly, the term with u t and u b or u t double dot and u b double dot will be the other terms. So, now one can use these are the non-dimensional parameter. For example, one can use this non-dimensional. So, this is static loading. So, which is equal to P 0 bar equal to P 0 L square by E, where E equal to E t I t plus E b I b. So, E t the Young's modulus of the top layer, I t is the moment of inertia of the top layer, E b the Young's modulus of the bottom layer, and I b is the moment of inertia of the bottom layer. So, this will give the non-dimensional static load factor. So, similarly, P 1 bar will be P 1 L square by E, where E is already it is described. So, this is the non-dimensional dynamic load factor, and one can non-dimensionalize the time also. So, taking this time T 0. So, one can take this T 0 equal to, so T 0 equal to m L fourth by this E t I t plus E b I b root over. So, taking this non-dimensional time. So, one can write this omega bar equal to omega T 0, and this mass ratio one can write m q by m. So, Q can take the top layer and bottom layer. So, m is the total mass of the system, and one can take this phi t equal to E t A t L square by E, and zeta c equal to, so zeta c equal to G c star A c L square by E. So, it may be noted that this for viscoelastic layer, as the viscoelastic layer, as the core is a viscoelastic layer. So, the shear modulus will contains the storage modulus and the loss modulus, or one can write this using this complex number G c into 1 plus j into eta c, where G c is the storage modulus and eta c is the loss factor. So, one can take this loss factor, and this is the storage modulus, storage shear modulus. So, this is the storage shear modulus, where j equal to root over minus 1. This is the, these two represent the imaginary quantity. So, the coefficient of the shear modulus of the viscoelastic layer can be written using this complex number G c into 1 plus I eta c, and we are non-dimensionalizing this x term, that is the displacement x bar equal to x by L, time non-dimensional time t bar equal to t by t 0, u bar equal to u by L, and w bar equal to w by L. So, using these non-dimensional parameters, so we can write the previous governing equations. So, in these forms. So, this is the equation in terms of W t. So, this equation contain start with the terms W b. So, W t, W b and U t, U b. So, we will have 4 equations. So, which are derived from this by using this Hamilton principle and using this non-dimensional parameter. So, now taking this W t in this form, writing or taking few modes of the system. So, as this is a continuous system, so one can have infinite degrees of freedom, but for analysis purpose we can truncate this system to a few finite degrees of freedom. So, let us take first n degrees of freedom of the system. So, by taking the first n mode of the system, so we can write this W t bar equal to summation m equal to 1 to n Fm t bar Wm x bar. So, here Fm is the time modulation and Wm is the shape functions of the system. So, the shape functions depends on the boundary conditions. So, we can see for or we can study the system for different boundary conditions. Similarly, this W b bar can be written. So, W b bar can be written by using this F q and W q. So, one may note that here m is taken from 1 to n and next parameter we have taken q equal to n plus 1 to 2 n. Similarly, for u t we have taken this parameter from 2 n plus 1 to 3 n and for u b we have taken this 3 n plus 1 to 4 n. So, we will have 4 n state vectors present in this equation motion. So, we can have 4 n state vector. So, now substituting these equation W t bar, W b bar, U t bar and U b bar. So, these equations all with multi modes. So, by substituting these equations in our previous equations, so these two and these two. So, these 4 equations. So, now substituting these in this equation and applying Galerkin method. So, we can write this equation in this form. So, already we know. So, this equation is in the form of Matthew-Wheel equation, but here unlike in case of Matthew-Wheel equation which is written for the single degree of freedom system. So, this equation is written for a multi degree of freedom system. So, where this F contain, so F is 4 n cross 1 vector. So, here we can have M as the mass matrix, F as the time modulation, K is the stiffness matrix, P 1 cos omega t into F equal to phi. So, phi is the null vector, P 1 bar already we know. So, this is the load parameter, dynamic load parameter, and omega bar is the external frequency acting on the system. So, here it may be noted that this term, this P 1 cos omega t, that is the time varying periodic term, is a coefficient of this F. F is the time modulation. So, which will be found, which will be used to find the response of the system. So, as this term is a coefficient or parameter of this F term, that is why this system is known as a parametrically excited system. So, this is known as a parametrically excited system as. So, this is a parametrically excited system with. So, we have 4 n equations. So, these contain 4 n equations, unlike the simple single degree of freedom systems what we have studied earlier. So, in this case also we can non-dimensionalize this mass and stiffness matrix and this load vector, and we can have this uncoupled equation which will be similar to that of a single degree of freedom system. Then after non-dimensionalizing or after uncoupling these equations, when we will get 4 n uncoupled equation, then we can individually apply these methods what we have studied for finding the instability regions. So, now, so here this M can be written in this form. So, M equal to M. So, one can write this M 11, M 12, M 13, M 14, M 21, M 22, M 23, M 24. So, these correspond to this W t, W b, U t and U b. So, that means, this will be W t double dot terms will be multiplied with this and W b double term. So, W U t double dot and U b double dot. So, in that way, so we have, so this each will be of 4:4 and so we can each will be of. So, depending on the number of modes we have taken, so each submatrix can be determined. So, similarly, this stiffness can be written in this form K 11, K 12, K 13, K 14 up to K 44. Mass matrix M 112, M 14. Similarly, this H contain this H 11, H 22 all other terms are phi, that means null matrix. And here it may be noted that this k, that is the stiffness k, which is coefficient of f, is nothing but it is equal to k 1 minus p 0 bar into h. So, it may be noted that this term, so this term comes from the stiffness, but this term is coming from the static loading. So, static loading. So, that means the static loading influence. So, the static loading influence the stiffness of the equivalent stiffness of the system, and one can find the equivalent stiffness of the system, and one can find similarly one can find the modal frequencies for this system. So, modal frequency can be obtained by finding this k inverse m. So, let us first see what are these terms. So, what M11 stands for. So, all these terms can be written, for example, M11 I j, that means I equal to 1, j equal to 1 also one can take, or this I and j vary from 1 to 4. So, this M11 I j can be written as this is m t bar plus m c bar by 3 integration 0 to L W m t into W m I into W m j into d x bar plus m c bar by 12 d t by L square integration 0 to L W dash m I into W dash m j d x. So, this dash is differentiation with respect to x. Similarly, this is plus m c bar by 576 into d t by c into 1 plus d t by c into c by L to the power 4 into zeta c by phi c into integration 0 to L W m I. So, this is double dash. So, single dash is differentiation, single differentiation with respect to x, and this double dash is double differentiation with respect to x. Similarly, one can find M12 using this expression, M13 I j can be found from this expression, and M14 I j can be found from this expression. So, one can find this mass matrix using these expressions which are obtained by using method of multiple scale. So, these are up to M44. Similarly, one can find this k11 after finding k11, k12, k21, k22, then up to k44. So, one can find this mass matrix and stiffness matrix by using. So, by using the load vector also. So, here H11 can be written as W m I dash into W m j dash d x bar, and this H22 equal to integration 0 to L W q dash into W q j dash into d x bar. Here it may be noted that, so we are using m. So, we are using, so from this one may note that we are using m for T, that is top layer, q for bottom layer, r for the, so these m and q are for the transverse deflection, and r and s for the axial deflection of the beam. So, in this way we can write the equation motion and find these coefficient by using these integrals. So, here one has to note, so what is the expression for W t, W b. So, the expression for these phi terms one has to see. So, these expressions actually are obtained from the eigenvalues of the corresponding boundary conditions. So, now one can, after getting these equations or after getting these coefficients, one can find this mass matrix and stiffness matrix by integrating these terms, and after finding this mass matrix and stiffness matrix, one can find this T matrix, that is known as the dynamic matrix. So, T is the dynamic matrix which can be written as M inverse k. So, this is the dynamic matrix. Now, by finding the eigenvalue of this dynamic matrix, that is M inverse k, so one can get the eigenvectors and eigenvalues. So, taking this, assuming these are distinct, so one can use or one can transform the original equation to another form, that is uncoupled form by taking this transformation. So, by taking f equal to t into u, where t is the normalized, t is the a. So, let us a is m inverse k. So, we can find the eigenvector. So, T is the modal matrix which contain the eigenvectors. So, these are the eigenvectors corresponding to different modes. So, T is a normalized modal matrix. So, if we are using T as the normalized modal matrix and then by taking this f equal to T into u, that means we are transforming this coordinate from f to u. So, then we can write this equation in this uncoupled form. So, we can write the original equation in this uncoupled form like this, that is u q double dot plus omega square omega q star square q plus 2 epsilon cos omega bar t into summation p equal to 1 to 4 n into b q p star into u p equal to 0. So, where q equal to 1 to 4 n are the 4 n number of generalized parameters which depends on the modes of the system. So, u is a new set of generalized coordinates we are using here. So, in this way we are transformed this coupled equation for the sandwich beam to a set of uncoupled equation, and in this uncoupled equation one can note that this term. So, this term, the coefficient of u p is a periodic term, that is why this equation is a parametrically excited system, but here we have a number of forcing term associated with this term depending on the number of modes we are taking in this solution. So, now to find the instability region, so here we can follow the method developed by cytoatomy. So, for Matthew-Hill equation with complex coefficient, and we have this case has also been used extensively by Ray and Core So, in their work they have used extensively this method, also the work by Core and Sujata. So, this method developed by Saito and Otomi, and so this method is developed by Su, but used for the parametrically excited system by Saito Otomi for viscoelastic or equation with complex coefficient. And so, in this case this W q star square, which is the distinct eigenvalues of m inverse k, and B q star. So, this is a complex number. So, which is coefficient of u p. So, here B q star are the elements of this B matrix. So, where B matrix is nothing but minus T transpose T inverse into M inverse into H into T. So, here we can write this W q star as W q real part plus W q imaginary part. Similarly, B q star we can write as B q real part, B q p real part plus B q p imaginary part. So, writing these eigenvalues and these B terms in their real and imaginary parts. So, we can find the region of instability. So, for simple resonance case, or for the principal parametric resonance case. So, we can write this expression in this way, that means the transition curve can be obtained from this equation, that is W bar by 2 mod of W bar by 2 minus omega mu r less than equal to 1 by 4 x mu, where x mu can be written in this way. So, this is equal to 4 epsilon square B square mu r plus B square mu I. So, this is the real part, this is the imaginary part, by omega square mu r minus 16 omega square mu I. So, root over. So, this is for the principal parametric resonance case. So, here omega bar by 2. So, in this case it may be noted that the resonance will occur at a frequency twice that of the natural frequency. That is why, so one can take this omega bar by 2 minus omega mu r. So, this should be equal to, for transition curve it will be equal to 1 by 4 x mu. So, taking or finding this mu value, so one can plot the instability region. Similarly, for combination resonance of some type, so this equation is in this form, that is omega bar minus, so this is some type omega mu r plus omega nu r, mod of this should be less than x mu v. So, when mu not equal to v, so this will be equal to, so we can have this, when mu equal to v we have the simple resonance case, when this is not equal to this, then only we will have this combination resonance of some type. So, in this case this x mu v can be written in this form. Now, for the difference type also we can have this expression. So, using these expressions now for, so let us take a physical example and we will see how we will get the instability region. So, here we can take these W m, W q, U r and U s as the shape functions of the corresponding Euler-Bernoulli beam with boundary condition. So, for example, in case of the simply supported end conditions, so we can take this W m x bar equal to sin m pi x bar. Similarly, W q x bar, these are the transverse direction thing. So, W q x bar equal to sin q bar pi x bar. Similarly, U r x bar equal to cos r bar pi x bar and U s x bar equal to cos s bar n pi x bar. So, these equations will be used in those integrations to find this mass matrix and stiffness matrix of the system. Similarly, one can use this equation for the clamped pin end condition. So, this is for simply supported. Simply supported means this end condition will be like this. So, this is simply supported, and in case of clamped pinned, so one side is clamped and other side is pinned. So, this is for clamped pinned end condition. So, one can use this W m in this. So, by using this polynomial one can use W m, U r, W q and U s. So, these equations have been followed from the work of Ray and Core paper. So, it has been followed from this paper on the sandwich beam vibrations. So, they have used this classical theory to find the response of this or the parametric instability region. So, this is for clamped free end condition. So, in case of clamped free end condition, so this is clamped and this is free, or this is a cantilever type. So, in this cantilevered sandwich beam, this is a cantilevered sandwich beam. So, in this case one can use these equations, and in case of clamped guided, so one end can be guided also. So, in this case one end is clamped and other end, so other end, so we have a sandwich beam and other end is guided. That means, so we have a guide, so it is constrained to move. So, it will be constrained to move in this guide. So, in that case we can have either we can have a guided this way, or we may. So, the guided condition we can have, so it can be, so it is constrained to move in this guide. So, as we are considering the transverse vibration, so it is constrained. So, this sandwich beam is constrained to move in this direction. So, we have a roller support. So, this is for the clamped guided end condition. So, for the clamped guided end condition you can use this W m, W q and U s, U r, U s. So, in this way, and so let us say see some results. So, in this case this work is taken from the work by N. Mohindra, a MTech student, of Mechanical Engineering Department, IIT Guwahati. So, these numerical results and discussion have been taken from his MTech thesis, and this work also has been published in some conference and journals. So, this is for a unsymmetric sandwich beam. So, the length, let us take this length, width, core and thickness in this way, and here 3 different types of core has been taken. So, one is H45 foam core, H80 and H250. So, whose loss factors are taken 0.1, 0.05 and 0.1. So, the non-dimensional static load factor is taken 0.1. So, these are material properties for aluminum, steel and H45, H80 and H25. So, Young's modulus. So, Young's modulus, then shear modulus, this is the storage modulus has been taken. So, it may be noted that the storage modulus for these materials are taken very less. So, while for storage modulus for aluminum is of the order of 10 to the power 9. So, here it is of the order of 10 to the power 7. So, the density, one can see the density of this H45 is near to 45 kg per meter cube. Similarly, H80 it is equal to 80 kg per meter cube, and for 250 it is equal to 250 kg per meter cube. So, taking these values, so one can plot, so this instability region. So, these are for the simply supported case. So, for different case and for different core and material one can find, for different end conditions one can find these instability region. For example, let us take this instability region here. So, here if one take a point here, here and here. So, this point corresponding to A. So, if one plot the time response, so it will lead to a stable condition. So, it will finally lead to a stable condition which is 0 trivial state. Similarly, for this C also it will lead to trivial state, and for one can take B, then the response actually will grow. So, the response will grow and finally, the systems will be unstable. So, this way one can find the instability region for different types of core and for different end conditions. So, this has been shown in the so in case of unstable region. So, in case of stable region, so it will come to this 0 position in case of stable, and in case of unstable it will grow and it will finally. So, one can have unstable region. So, in this way one can study the parametric instability regions, and one can obtain the response of the system by using the equations developed here in this, or the equation used in this work. Also, one can take different type of core material. For example, one can take this magnetorheological elastomer core for finding the instability region. Also, the skin material may be changed. Instead of taking metallic skin, one may take this composite skin or functionally graded skin to find the parametric instability region of the sandwich structure. So, this is one of the application of the parametrically excited systems we have seen today. So, next 2 classes also we will study about 2 more applications. So, in tomorrow class we will study about the parametric instability region of an axially loaded elastic beam and elastomagnetic beam, and in the last class or in the third class in the series we will study the parametric instability region with internal resonance of the system. Thank you.